Now that we have discussed some tools like simplicial complex and we defined how we can compute the homology group, we want to jump into examples. But as it turns out that the definition we saw for the homology group over here, this one, sometimes it becomes complicated to use this prescription to compute the homology group. So what we are going to do is that we're going to state another theorem that is called the fundamental theorem of homomorphism that will help us in computing the homology groups. And to do that, first we need to define what is a kernel and image of a group. So we want to talk about kernels and image of a group. We're just going to give the definitions and then we're going to state the fundamental theorem of homomorphism. So what is a kernel and what is the image of a group? That's the question we ask. So let F be a map from group G1 to G2, and this map is a group homomorphism. That means this map preserves the algebraic structure. Then the kernel is defined as the following. We write the kernel as ker F defined as X, and this X will belong to my group G1, and when this group homomorphism acts on this X, it maps this X to the identity element on group G2. This is the definition of a kernel. And now we talk about the image, and the image is defined as img. That means the image of F is some X where X belongs to F of G1, which is a subset of G2. That means you are taking the whole group and you are acting F on G1 and it's producing elements of G2, and all these elements will form a subset of G2. This is the image of a group. And now we're ready to define the fundamental theorem of homomorphism. Fundamental theorem of homomorphism. We will accept it without a proof for now. So let us state the theorem first. Let F be a group homomorphism from G1 to G2, be a homomorphism, then G1 mod the kernel of this map is isomorphic to the image of F. This theorem will help us a great amount when we are trying to compute the homology groups. And the way we use this theorem in our computation of homology is the following. So let me write that down. The way we will use this theorem to homology computation or homology group computation is the following. So let's say this is my nth homology group over some simplicial complex K. It will be defined with Set of K modded with the boundary group, and this boundary is nothing but the kernel. Why? Because what is a boundary? Like if you have the boundary operator, and if something is your boundary, you add the boundary operator onto that boundary and you get a 0. That is like an identity element over Z. For now, we can think of it like that way. So similarly, the homology group is nothing but the image of the homomorphism. So we write it as Zn of K kernel of F, which is just the image of F according to this theorem over here, the fundamental group of homomorphism. So in summary, we can write it as this. It should be equal, and this should be isomorphic to Im of F. And when we talk about isomorphism in some loose sense of manner, you can think of that these two groups are essentially the same thing. So now that we have discussed all the tools, let us jump into examples. So we will now consider computation of homology groups. So